Good afternoon, class. We are looking at exam 4 review, chapter 4, application of differentiations. Here's part 3, covering the definite integral and the fundamental theorem of calculus, or FTC. Section 5.2, the definite integral. Suppose a continuous function f is defined on the closed interval of a to b. The interval is divided into n subintervals. Delta x equals b minus a over n, and x sub 0 is a, x sub 1 is a plus delta x, so on and so forth. Then a Riemann sum associated with f is the sum that we have here. So the integral of a to b f of x dx is the limit of the summation of f of x sub I delta x as I goes from 1 to n, as n approaches infinity. In other words, the limit as n approaches infinity of the bracket f of x sub 1 delta x plus all the way to f of x sub n times delta x, where delta x is, of course, b minus a over n, and x sub I equals a plus I delta x. We had discussed this concept previously, where x sub I is any point chosen in the interval of a sub I minus 1 and a sub I. Let y equals f of x be continuous and non-negative over an interval of a to b. A definite integral is the limit as n goes to infinity. Equivalently, delta x goes to 0 of the Riemann sum of the areas of rectangles under the graph of y equals f of x over a to b. In other words, when we take this limit, this becomes the area under the curve. Okay. So the area under the curve is exactly equal to this limit as it has been mentioned. So it's mostly something we have seen. Now, I want to go over the concept of a definite integral by dissecting every part of it. The integral of a to b f of x dx. Let's see what each symbol is. This is called the integration symbol. This symbol was introduced by Leibniz and is called an integral sign. It is an elongated S and was chosen because an integral is a limit of sums. Lower limit of integration, A. Upper limit of integration, B. F of x is the integrand. Dx, variable of integration, sometimes we call him dummy variable. It is called a dummy variable because the answer doesn't depend on the variable chosen. The dx is simply the dx simply indicates that the independent variable is x. The integral of a to b f of x dx is a number. It doesn't depend on x. You could use any letter in place of x without changing the value of the integral. So the integral of a to b, f of x dx or f of d dt or f of m dm, they all are the same. Or its approximation, the integral of a to b f of x dx is almost equal to the summation of I going from 1 to n of f of x sub I delta x, which means f of x sub 1 delta x all the way plus all the way to f of x sub n times delta x. This is an approximation. This sum is called a Riemann sum. It becomes precise, it becomes exact if you take a limit and you let n go to infinity. So the area is the limit of summation I going from 1 to n of f of x sub I delta x as n goes to infinity. All right. So the integral of a to b f of x dx is the limit of the summation f of x by delta x as I goes from 1 to n and as n goes to infinity. Now we want to express this limit as an integral on the interval of 0 to pi. So in essence, it means we're going to compare these two. So we are going to compare the integral of a to b f of x dx with this limit that we have here in the interval of a to b. So when we do that, f of x of I that is x sub I cubed plus x sub I sine of x sub I. So simply put, it means then f of x must be x cubed plus x sine x, and the integral of a to b, they said from 0 to pi. So a is 0, b is pi. This part is given, a and b. So we write the limit of x sub I cubed with the plus x sub I sine x sub I times delta x, as we take the sum from I equals 1 to n and we take a limit, is the integral of a to b, 0 to pi, x cubed plus x sine x dx. In other words, we can go from the limit to the integral format and vice versa. Now, this example, expressed as an integral, the limit as n goes to infinity of summation of I going from 1 to n sine 2 pi I over n times 2 pi on 2 pi over n on the interval of 0 to 2 pi. First and foremost, and quickly, this means a to b. Okay, so we can see a is 0 and b is 2 pi. So let's compare. Let's compare these two. So as we mentioned, a is 0 and b is 2 pi. Well, delta x is b minus a over n. B minus a over n is 2 pi over n. And x sub I is a plus I delta x is this one, everybody. X sub I is a plus I delta x is 2 pi I over n. So this is f of x sub I sine of 2 pi over n. So simply put, the function f of x is sine of x on the interval of 0 to 2 pi. Therefore, the limit that then goes to infinity of summation of I going from 1 to n sine of 2 pi over n 2 pi n is the integral of 0 to 2 pi sine x dx. Use summation formulas to compute the integral of 0 to 2 1 minus x squared dx. Well, we write the integral of a to b f of x dx is the limit of f of x of I delta x as I goes from 1 to n. And so we are going to follow that. And there are a few things that we need to remember. First of all, the definition of the area using the limits. Then delta x is b minus a over n. Then x of I is a plus I delta x. And these are some information that are handy. For example, summation of 1 is n as I goes from 1 to n. Summation of c, you can put the c out times 1, it's nc. Summation of I is n times n plus 1 over 2. Summation of I squared is n times n plus 1 times 2n plus 1 over 6. And I cubed is n squared, n plus 1 quantity squared over 4. We're going to use those in a moment, but for now, let's see what the function is when you're looking at this integral. Then f of x is 1 minus x squared. A to b, that means from 0 to 2, a is 0, b is 2. So I hope that's clear to everybody. So that's the given. Now we say delta x is b minus a over n. So that means 2 minus 0 over n. X of I is a, 0 plus I times delta x, which is 2 over n. And therefore 0 plus 2i over n is 2i over n. Now over here, we are going to evaluate this limit. To evaluate the limit, I want you to just look at this piece. We are going to write this, simplify this, and then put it into the limit. In other words, then apply the limit. So what is summation of f of x of I delta x? You're going to replace f of x of I, and you're going to replace delta x. Delta x, you replace it with 2 over n. What is f of x of I? Well, if f of x is 1 minus x squared, f of x of I would be 1 minus x is going to be replaced by x of I, which means 2i over n quantity squared. So f of x of I, because f of x is 1 minus x squared, f of x of I is 1 minus 2i over n quantity squared. So into this, we replace the f of x of I with that, and then delta x with 2 over n. So let's raise this to the power of 2, everybody, and this is 4i squared over n squared. You multiply these two, we get 2 over n. You multiply these two, we get 8 I squared over n cubed. We are going to simplify this as much as possible. So we are going to make up two limits. One limit involves 2 over n minus the other one involves this piece. And we are going to take out whatever we can. Remember, the limit applies to I. So this part is 2 over n times summation of 1. This one is 8 over n cubed times I squared. So I hope you see what I'm doing here is elementary algebra. So one more time, 2 over n. So summation, as I goes from 1 to n, we put 2 over n out and 1 inside. That's in essence using this concept. This one, the I squared remains, so minus 8 over n cubed comes out. So we need to find this, which is this one. We need to find this, which is this one. So plug it. So we are going to write 2 over n times n minus 8 over n cubed minus 8 over n cubed over times this fraction. Now, first of all, everybody can see this is 2. Secondly, the denominator here is 6n cubed. The numerator, please understand that when we multiply this, the first term is 2n cubed, and it really doesn't matter what the rest is. And I'll tell you why in a moment, why the rest is not important. But why is it 2n cubed? I want to make sure everybody understands. This is n times n squared times 2n cubed. So this is 2. This is minus 8 times 2 minus 16n cubed plus some other stuff and over 6n cubed. Now, so this integral is the limit of this, and we are going to put that in there. Now, because n goes to infinity, of course, 2 doesn't change. But why is it that I didn't write the rest of them? Because when n goes to infinity, the leading terms take over. And I hope you see that this part takes over. The rest go to 0 because the degree is less than n cubed. Remember, you are evaluating a limit, you divide by highest degree term in the denominator, so that gives you minus 16. The rest of them don't do anything, so 2 minus 16 over 6. And this is 8/3. So 2 is 6/3 minus 8/3 is negative 2/3. Now, what I want to make a point of is that the integral of a to b f of x dx represents an area under a curve if the function is positive. Otherwise, it's the difference of areas. Given f of x equals x cubed minus 6x, evaluate the Riemann sum taking the sample points to be right endpoints. A is 0, b is 3, n is 6. And the idea is the area is being approximated by a Riemann sum because n has a value. It doesn't go to infinity. I hope you remember we've done this concept. So in essence, it's f of x sub 1 times delta x plus f of x sub 2 times delta x all the way to the last one, f of x sub n times delta x, and of course delta x as always, b minus a over n. So you can graph the function The function is x cubed minus 6x. A is 0, B is 3, and n equal to 6. So you can see that we want to go from 0 to 6. 0 to 3, my apologies. Let me just put 1 and 2 here. 1, 2, 3, okay. And A is 0, B is 3, N is 6. So we cut it into 6 equal parts. Delta X is B minus A over N, which is 3 minus 0 over 6, or 1/2, or 0.5. So basically, A is 0, B is 3, and we cut this in 6 equal parts. We have 1/2, so add 1/2 or 0.5, then 1, 1.5, 2, 2.5, 3. And if you were to draw, it will look like this, meaning the width for all of them, 1, 2, 3, 4, 5, 6 rectangular strips, they have the same width, 1/2. And again, they don't have to, but it makes it easier this way. That's why we choose delta X as B minus A over N. To make sure they're identical, it makes it easier. Now, the first one, okay, so we are using the right endpoints. This is the right, this is, if we start with f of x of 1, we are using the right endpoints. If we start with f of x of 0, we are using the left endpoints. Normally, if they don't say anything, we start with the right endpoints, although they have mentioned right endpoints anyways. So it's delta x times f of 0.5 plus f of 1 plus f of 1.5 all the way to the end. In other words, the functional value of all these points, except the first one because it's a right endpoint. Okay, so this would be for the first one, second one, third one, fourth one, fifth one, sixth one. That's the idea, everybody. Which means you are going to put 0.5 into this, gives you an answer. 1, 1.52, and so on. Add them up, multiply by 1/2. I'm going to leave it for you to actually verify. When you do that, you get negative 3.9375. One more time. How do you find f of 0.5? Put it into this. 0.5 cubed minus 6 times 0.5. 1 is easy. 1 cubed is 1 minus 6 times 1. 1 gives you 5. So this would give you 5, for example. Okay. 2 is also easy. 2 gives you 2 cubed. 8 minus 12 minus 4. So on and so forth. Okay. So you can easily put it in. Evaluate it. Okay. And you end up with a negative. Now, it's important to understand the meaning of a negative. Again, it's the difference of areas. So in other words, I hope you recognize this. The area is larger than this. Therefore, because it's below the x-axis, this will take over and makes it negative. So it's the difference of areas. So note, this value represents the difference of areas, and I can't emphasize this enough. We want to evaluate the integral of 0 to 3x cubed minus 6x, where, again, I'm reminding you of the definitions, summations, and so forth. So what is the function, everybody? X cubed, f of x equals x cubed minus 6x. What is A? 0. What is B? 3. Okay. So In other words, we are looking at the same question, but this time we want the actual area, and that means it's not not an approximation, it's going to be an exact. So we are looking at the same situation, and we are going to find this exact area, and the final result will be the difference between the two. Okay, everybody? So delta x is b minus a over n, 3 minus 0, that means 3 over n, and x sub I is a, which is 0, plus I times delta x. So I times 3 over n. So 3I over n. So this integral is precisely equal to this limit, and therefore we are going to write this limit in the following manner. The limit as n goes, and as n approaches infinity, of summation of I going from 1 to n, f of x sub I. Well, here's f of x. If I want to replace the x with x sub I, that means this one is 3I over n, okay? And delta x is 3 over n. At this point, I'm going to evaluate and simplify this expression and finally put it into a limit, okay? So what is f of x is this one. F of 3I over n would be 3I over n quantity q minus 6 times 3I over n, and then close the bracket times 3 over n. So this part is this. Now, this is 3 cubed, 27 over n cubed times I cubed minus 6 times 3 minus 18 over n times I. Now I'm going to multiply by 3. If I multiply these two, everybody, I get 81 over n to the power of 4. I can take it outside the limit. If I multiply these two, I get 54 over n squared with the negative sign. I take it outside the limit. So I hope everybody can see what I'm doing. I'm doing elementary algebra, everybody. And I'm getting this one ready to use the I cubed, and this one ready to use the I. Let's do it. Let's keep this and replace this with n squared times n plus 1 quantity squared over 4 minus 54 over n squared. Let's keep that, and square root of I replace square root of I, as I goes from 1 to n, is replaced by n times n plus 1 over 2. And now we are going to simplify. Okay, and here's how we simplify. First and foremost, this one, everybody, is n squared plus 2n plus 1. I'm just interested in the first term. Why? Because the denominator is 4n to the power of 4. So if this is 4n to the power of 4, and this is n to the power of 4, this is 81n to the power of 4. Why the rest are not important? Because the degree of the denominator is 4. The degree of the leading term for the numerator is also 4, and the rest of them go down. This one is n squared. Of course, the next one is n. But again, this is the only one that matters because the denominator is 2n squared. So I'm going to write it in this fashion. I want everybody to see, again, the reason I'm writing the leading term for the top only because the rest of them have a degree smaller than 4 for the first fraction. And this one, there's only one more, which has a degree less than that. So as you take the limit, so this integral, the integral of 0 to 3x cubed minus 6x dx is the limit of this expression as n approaches infinity. And so what happens is that this one, I hope you see, you get 81 over 4, and this one you get 54 over 2. So 81 over 4 minus 54 halves, or 108 over 4. So the denominator is 4, the numerator is 81 minus 108, which is minus 27. And this is the exact area. Again, more precisely, the difference of areas. Okay, this minus that. And that's an exact answer. Now, again, just for the sake of argument, the previous page gave us almost -4, and the reason it was off, we only used n equals 6, and it should be off, and it was. But if we add it to n would be better, and of course, as n goes to infinity, it gives you an exact answer. Now, evaluating integrals using signed area. Use the signed area interpretation of definite integral to compute the integral of -2 to 2x dx. We want to discuss that, and you'll see how interesting it becomes. First and foremost, what function are we dealing with? The function f of x equals x, the interval of -1 to 2, a to b. Now, f of x equals x or y equals x is the line that goes through the origin. This is y equals x. And from -1 to 2, that means from here to here, over here, and over here. I hope you see that the concept of signed areas, as we discussed, the integral represents the difference of the areas if some is positive, some is negative. It represents the actual area under the curve if the entire function is above the x-axis and it's positive. So having said that, you can clearly see that we can calculate this because it's a geometric shape we are familiar with. This is a triangle, so is this one. And so area of a triangle has the formula 1/2 base times the height. So if you look at this point, the coordinates are 2, 2. So this distance is 2, so is distance. So the area is 1/2 of 2 times 2, or 2. And for the red one, this point has coordinates -1, -1, which makes this distance is 1, this distance is 1. And so 1/2 of 1 times 1 is 1/2. And therefore, the area would be 2 minus 1/2, which is 3/2. The integral of -1 to 2 of x dx. And that's fine. I want to show you what's coming up is one of those fundamental theorem of calculus that says if you want to evaluate the integral of f of x dx from a to b, this is a definite integral, this is a number, and it's capital F of b minus capital F of a. That means take the antiderivative and evaluate it at the end points. Their difference gives you the answer. The difference between what we just did and this one is that this will fail when we don't have a specific geometric shape, but this will always work. Okay, and so having said that, we are going to take the antiderivative of integral of x becomes half of x squared, and we're going to evaluate it from the lowercase minus 1 to uppercase 2. And so 1/2, you plug in 2 squared, and you plug in -1, becomes 1. Again, this is the way you evaluate it. So 1/2, plug in 2, you get 2 squared, 4, plug in negative, minus, plug in -1, you get +1. So 4 minus 1 is 3, times 1/2 is 3/2, and that's exactly what we have here. So again, it's pretty straightforward, everybody. As an example, I want you to practice by graphing and using signed areas to show that the integral of -4 to 1 is of 6x dx is minus 45. In other words, show it with graphs, just the way we did it here, and show it with the this is one of the FTC's fundamental theorem of calculus for practice, and you show it that they are identical. Now, we want to use geometry to evaluate the integral of -3 to 3 square root of 9 minus x squared dx, everybody. Well, the function is square root of 9 minus x squared, and the interval is -3 to 3, obviously. What type of a graph is this? Let me remind you, when you have a circle centered at 0, 0, the formula is x squared plus y squared equals r squared. As the different center would be x minus h squared plus y minus k squared equals r squared, where the center is at h and k. So this is the synapse of what we just said. And the area, of course, equals pi r squared. Circumference is 2 pi r. Now, y equals square root of 9 minus x squared. If I square both sides, that gives me y squared is 9 minus x squared, which gives me this one, which is a circle centered at 0, 0 with the radius 3. And I hope you remember that when you have an equation of a circle, if you solve for y, it gives you two answers. Okay. It's the top half and the bottom half. And if you solve for x, it gives you the right and left half. So y equals square root of 9 minus x squared is the top half. In other words, this portion. And this one would be this one. And so the graph is a semicircle, with that being an x, the right half and the left half. So is a semicircle with the radius of 3. That's what we have. So if the area is pi r squared for a circle, for semicircle is the same thing times 1/2. So 1/2 pi and r is 3. So this is 9 pi over 2. So precisely 9 pi over 2 is the area. So we can't come up with the answer using information from calculus 1. This can be done using calculus 2. We're not going to discuss that. That's why you need to know definitely how the area thing works. Now, properties of definite integrals. Let f and g be continuous functions over the interval of a to b. Definite integral at a point. The integral of a to a f of x dx is 0. Well, I hope you see why a point doesn't cover any area under a curve, because delta x b minus a over n becomes 0. A minus a over 0. That's one way to look at it. Sum and difference rules. The integral of a to b f of x plus minus g of x d of x is the integral of a to b f of x dx plus minus the integral of a to b g of x dx. And it's clearly, if this is f, this is g, and this one can see the sum or the difference of it. Scalar rule, constant multiple. The integral of a to b c f of x dx, you can take the c out. In other words, if this is f of x and this is 2 times f of x, so the area becomes twice as large. Dominance, if f is larger than g, as long as it's within the interval of interest, the rest is not important. In other words, from a to b, then the integral of a to b f of x dx must be greater than the integral of g of x dx from a to b. So, in other words, if f is at top of g entirely, then the definite integral must be large. Bounding max minus mean. If m is less than or equal to f of x less than or equal to m. And normally we use lower m to represent the minimum for the function and capital M for the maximum. As we go from a to b, if we multiply both sides by b, all sides by b minus a in essence, the left side and the right side, we get m times b minus a. This is capital M times b minus a, and it's this integral is in between because here's the minimum. B minus A is the width and the height is M. For the maximum, capital M is the height. For y equals f of x, the height changes. So it's in between. This is a very important property known as splitting property. A to c f of x dx is a to b f of x dx plus b to c f of x dx. Notice it starts with A and ends with C. In between, these two must be identical, okay? And so the integral of A to B and then B to C is the same as the integral of A to C in one shot. That's the idea. Then we have a few more. Opposite rule. The integral of A to B f of x dx is minus the integral of B to A f of x dx because, again, delta x is b minus a over n, and it will be negative if you go the opposite. The integral of a to b c times d of x is c times b minus a. And if f is larger than or equal to 0 from x equals a to x equals b, then the integral must be positive. In other words, if the function is positive, so it's the integral because it's above the x-axis. So because it represents the area under the curve when it's positive. Let's look at a couple of examples quickly, everybody. The integral of 1 to 3, 3f of x dx. What is given? The integral of 1 to 3 f of x dx is 6. The integral of 3 to 7 f of x dx is 9. The integral of 1 to 3 g of x d of x is minus 4. You want to evaluate the function. So basically, you are going to take the 3 out. Then it becomes identical to this, right? So 3 times that. The integral of 1 to 3, 2f of x minus 4g of x dx. We are going to split this into two integrals in the following manner. We take the 2 out, we can take the 4 out. This part We replace it with 6 and this part with 9. No, g of x, I'm sorry. G of x is with minus 4. So we get 12 plus 16 equals 28. One to 7. Well, we're going to write 1 to 3 plus 3 to 7. 1 to 3 is this number. 3 to 7 is this number. You add them up. The integral of 3 to 1 f of x dx. Well, it's the same as this one, but you know, the limits of 1 to 3 are changing to 3 to 1. So it's minus this integral. Therefore, minus 6 is the answer. The fundamental theorem of calculus, or short FTC. The fundamental theorem of calculus is appropriately named because it establishes a connection between the two branches of calculus, differential calculus and integral calculus. It gives the precise inverse relationship between the derivative and the integral. The d dx of the integral of a to x f of t dt is f of x, which means if you integrate the function and then differentiate it, you get the function back evaluated at this upper limit. So the FTC theorem of calculus. Suppose f is continuous on a to b. If g of x equals the integral of a to x f of t dt, then g prime is f of x. Okay, or what we just mentioned. The integral of a to b f of x dx is capital F of b minus capital F of a, where f prime is lowercase f. Okay, so those are the ones that we are referring to, everybody. The integral of a to b f of x dx is capital F of b minus f of a. The derivative of the integral of a to x f of t dt is f of x. And so let's quickly look at a very simple example. The integral of x to the power of 7 dx as we go from 0 to 1. So the integral of 0 to 1. You know how to find the antiderivative is 1 over 8 x to the power of 8. So plug in 1. So 1 over 8 times 1 and then plug in 0. Okay, and subtract it. You get 1 over 8. Now, tip, this is important to know. Even if we use another antiderivative and we write capital F of x plus c, notice I didn't put a constant here. In the evaluation theorem, the result will be the same because you get f of a b plus c minus f of a plus c. These two cancel each other. In other words, when you want to evaluate this, you don't write the constant because they cancel out. Please understand when we write x to the power of minus n, it means 1 over x. Therefore, it's a natural log. And we are going to evaluate it from 1 to 2. So it's ln of 2 minus ln of 1. We should know ln 1 is 0, so the answer is ln 2, and you keep it as an exact answer. If we look at the same thing, but different limits, now here's the difference, everybody. Over here, we had the absolute value. I don't have to have the absolute value here. Now, when I plug in, I must keep the absolute value because ln of minus 1 is meaningless. So ln of 1 minus ln of 2. And as you know, ln of 1 is 0. So we get negative ln 2 precisely. The integral of 0 to pi sine x dx. As you know, the derivative of sine is cosine, but the integral is negative cosine. So negative cosine from 0 to pi. Let's just evaluate the cosine and keep the negative out. Becomes cosine pi minus cosine 0. As you know, cosine pi is minus 1, minus cosine 0 is positive 1. So this entire thing is minus 2. This makes it positive. Evaluate the integrals. The integral of 0 to power 2, 1 plus cosine t dt. Well, first pay attention that the independent variable is t, therefore 1 doesn't give you x, it gives you t. And of course, the derivative of cosine is negative sign, but the integral is positive sign. So t plus sine t, we are going to plug in pi over 2, we're going to plug in 0. 0 and sine 0, they are both 0. So this is 0. Sine of pi over 2 is 1, so we get pi over 2 plus 1 precisely and leave it as such. Because we want an exact answer if possible. The integral of 1 to 4, 5x squared of x plus 3 squared of x dx. And whether we differentiate or integrate, the process is that we change this to x to the power of 1/2. And this is 1, 1 and 1/2 is 3/2, this one, okay? The reason why we want to get both of them ready for using the power rule. 1 over n plus 1 x to the power of n plus 1. So this becomes 5 over 3/2 plus 1 x to the power of 3/2 plus 1. This becomes 3 over 1/2 plus 1 x to the power of 1/2 plus 1. And of course, evaluate it from 1 to 4. This is 5/2. This is 2. 3/2. This is also 2. And so you're going to plug in 4. You're going to plug in 1. What happens when we plug in 4? 4 to the power of 5/2 means the square root of 4 to the power of 5. Which means 2 to the power of 5 is 32. 2 times that is 64. 4 to the power of 3/2 means square root of 4, which is 2, cubed is 8, times 2 is 16, and this one is 1, this one is 1. So you get minus 4, and therefore 76 is the final answer. Evaluate the integral. F of x is given as 2 when x is between -2 and 0, and 4 minus x squared when x is between 0 and 2. And we want to evaluate the integral of f of x dx from -2 to 2, so we cut it into two functions. From -2 to 0, we use this one. So the integral of -2 to 0, 2 dx. And from 0 to 2, we're going to use this one. So this one, 2x from -2 to 0, this one, 4x minus 1/3 x cubed from 0 to 2. Now we plug in 0, 2 times 0, minus, we plug in -2, minus 2 times -2. This one, 4 times 2, minus 1/3 times 2 cubed, and then 0 gives you 0. So this is what we get. Obviously, there's not much we have to do here. This is 0. So is this one. And this is just 4. This is just 8. This is 8, so minus 8/3. 4 and 8, 12. Minus 8/3. 12 is 36/3. Minus 8/3 is 28/3. So that's pretty straightforward. Find the derivative of the function g of x is the integral of 0 to x squared of 1 plus t squared dt. And this is one of those fundamental theorem of calculus, okay, that says the derivative of this function gives you this function back at x. So the d dx of the integral of a to x, f of t dt is f of x, okay? So we want to differentiate this, find the derivative. We want to differentiate this. So notice that this is f of t. So f of t is the square root of 1 plus t squared, which is a continuous function. And the reason it's a continuous function, because when we don't write the index is 2. As you recall, square root of x, the domain is what? 0 to infinity, because you have to say x is larger than or equal to 0. In this case, 1 plus t squared larger than or equal to 0. As you know, it's everywhere that is larger than or equal to 0 because it's 1 plus t squared. So in the worst case scenario, no matter what t is, this becomes at least 1. So that works. So by FTC, then the derivative, that means g prime or d dx of this is the same thing evaluated at x. So replace the variable with x according to this by FTC. G prime is square root of 1 plus square root of 1 plus x squared. It's my work, so we can continue. We want to differentiate this again using FTC first. Your function f of t sine t. Now, if the upper limit is just x, the independent variable, or any variable that just becomes independent and the derivative is just 1, that's what we have here. However, if you have a function of that, this is not x, this is a function of x, then the derivative of the integral of a to g of x, f of t dt, is f of evaluate the function, in other words, the composite function, at g of x and then times g prime of x. So with that would be sine of, replace the t with x squared and then times its derivative, which is 2x. One more time. Sine t, replace the t with x squared, and because this is a function of x times its derivative. This is actually by the chain. Let me show you a different method to see the proof actually. So in other words, ignore what we just did here. And of course, you put the 2x in front. You put the 2x in front. But the second method is to integrate this. We know how to, so never mind this part yet. We want to do this part. When we are finished with this part, we take its derivative. Okay, so let's do this. The integral of 1 to x squared sine t dt. the integral, as you know, of sine is minus cosine. So minus cosine t, evaluated from 1 to x squared. So plug in x squared minus plug in 1. Please understand that. This means minus cosine squared plus cosine 1. And cosine 1 is a number. So I want to differentiate this expression. When I want to differentiate this expression, let's see what we get. First of all, this gives you 0 because it's a number. Minus. The derivative of cosine is negative sine. It gives you minus becomes positive sine x squared. And by the chain rule times the derivative of x squared, which is 2x. I hope you can see that. It's fairly simple. So to recap, if you're taking the derivative of the integral of a to x f of t dt, it just becomes f of x. But if you're taking the derivative of f of t dt, the integral of a to g of x, then f of g of x times g prime of x. So same thing here. We want to take the derivative of the expression, and this is not x, this is a function of x. So f of g of x. So the function is tan t. F of t is tan t. So replace the t with x squared plus x, then times its derivative, which is 2x plus 1. Times 2x plus 1, and put the 2x plus 1 in front. And you're done. Now, what happens when, okay, so going back here, the lower limit is a number, by the way. Any number, it doesn't have to be 1. In fact, you see it says a here. That means any number, because ultimately when you put a number, you get a number, and the derivative is 0. So you're fine. But what happens when the lower and the upper limit are both functions? So we follow this. The derivative of the integral of f of t dt as we go from g of x to h of x, first we plug in h of x, so it becomes f of h of x times h prime of x, minus, then we plug in the lower limit, g of x, f of g of x times g prime of x. This h prime and g prime is by the chain rule. So in other words, first you put the sign, you get sine squared, times the derivative of sine, which is cosine, minus, then you put tan, you get tan squared, times its derivative, which is secant squared. So f of t is t squared, sine squared, times cosine x, minus tan squared x, times the derivative, which is secant squared. So it's very straightforward, everybody. The derivative of the integral of sine x to 1, the square root of 1 plus t squared dt. First and foremost, notice this is your function, f of t. So we have to go and plug in the limits, but the limit, the bottom one is a function, the top one is a number. So we are going to interchange them and make this negative. So this is minus the same thing, but the lower limit is 1 and the upper limit is sine. In essence, we are making it looking like that. And so minus, you put this one, sine x replaces the t, you get minus square root of 1 plus sine squared x. And now the derivative of sine x, which is cosine x, and you put that in front, and you get minus cosine x square root of 1 plus sine squared of x.